If a reaction is proceeding in this direction, we can say that the reaction will proceed in this direction also. So such a reaction is called as reversible reaction. Eventually what will be happening? The rate at which solid is getting converted into gas will be more. That is, forward reaction will be more. That is why you will be only able to see a small color here. We can say that the system has attained equilibrium when the rate of dissolution will be equal to the rate of crystallization. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So in today's session, we are going to study about what is equilibrium, the introduction to equilibrium and the classification of equilibrium, different types of equilibrium. In detail, we are going to study about physical equilibrium today, equilibrium in physical process, equilibria involving dissolution of solids or gases in liquids, as well as some general characteristics of physical equilibrium. Okay, so first of all, before moving on to these contents, okay, let's understand what is equilibrium. So let's take an example of a weighing balance, not the digital one, the old weighing balance. Okay, so in that you can see that there will be two plates on which you can put on weights, right? So if I have to measure some vegetable which is around 100 grams, then what do I have to do? On one side of the plate, I have to put a weight which is 100 grams. And once the weight of the vegetables and the 100 gram becomes equal, both of the plates will be in the same height or the same position, right? So this is how we balance it. Right. So in this position, we can say that both of them are in equilibrium. Right. So if at all assume that the weight was more than 100 gram, what would happen? The vegetables side would be little more down. Right. And this will be up. But if they are having both the same weight, what will happen? It will be in the same exact position. Right. So now we can say that they are in equilibrium. Okay, that is one example. Another example we can take is, let's assume or let's take one container in which I have water. Okay, and let's assume that it's a closed container. It is a closed container. Okay, so once we start heating this, what happens? The water will start boiling. And water will start boiling and it will get converted into, yes, water vapors, right? That is, from liquid phase, it gets converted into vapor phase, right? And at the same time, another process is also happening. That is condensation. That is, from vapor phase, it is getting converted back into liquid phase as well, right? From here, that is, from liquid phase, it is getting converted into vapor phase, and from vapor phase, it is getting converted into liquid phase as well, as it is a closed container, right? So in this case, after a while, if we are checking the mass or volume of the water, it will be the same. It will not have been, it must not have been changed, right? It will be the same, right? Because it is a closed container. So now we can say that it is also in equilibrium, right? Water, if we are taking it in a closed container, it is in equilibrium. How come? Yes, the rate or the speed at which the evaporation process is happening, the exact rate at which the condensation will also take place. Okay, both of this process is happening. Evaporation is happening as well as condensation is happening, and both of them are happening in the same speed and at the same time. So what happens? Eventually, we'll feel that there is no change itself which is taking place, right? We feel that there is no reaction taking place because both of them will happen at the same speed. Okay, so we can say that it is in equilibrium. Okay, so these are few examples of equilibrium. So now in detail, we are going to study about different types of equilibrium, what is physical equilibrium, chemical equilibrium, and different types in that as well. So then we'll get a better idea about what is equilibrium. So let's understand before that, what are the different types of reactions. One is reversible reaction and another one is irreversible reaction. So now out of reversible reaction and irreversible reaction, which reaction will show equilibrium? Okay, that means first let us move on with reversible reaction. So from the name itself, you can say what is reversible? Something which we can reverse it, okay, or else revert back. That means if a reaction is proceeding in this direction, we can say that the reaction will proceed in this direction also. So such reactions is called as reversible reactions, right? For example, let us take A plus B giving C plus D. So in that case, A plus B is the reactants. A and B are the reactants, right? A and B will combine and form C and D. So that is the forward reaction. We call it as the forward reaction. Okay. So it is a reversible reaction. So that means that C and D can also combine and form A and B. In that case, C and D will be the reactants and A and B will be the products. So that is called as the backward reaction. So this is your forward reaction and this is your backward reaction. So such reactions are called as reversible reactions, which can happen in both the directions. So a reversible reaction which can occur in both forward and backward direction is called a reversible reaction. Now moving on to irreversible reaction. Now what will be irreversible? Right, irreversible reaction means it can happen only in one direction, not in the both directions. A reaction which can occur only in the forward direction but not in backward direction is called a irreversible reaction, right? So in that case, A plus B gives C plus D. Okay, A and B will combine and form C and D, but the opposite will not take place. That's why you can see a single arrow here and a two half arrows here. Right, it is happening in both directions. That is why it is represented by two half arrows. This is the forward reaction and this is the backward reaction. Okay, so I hope reversible and irreversible reactions are clear for you. So where can you find equilibrium existing? That will be of course in reversible reactions, right? Yes, that means it should happen in the forward reaction as well as in the backward reaction, and both of them, if it happens at the same rate or same speed, we can say that they are in equilibrium, right? Okay, so let's understand the different types of equilibrium. One is physical equilibrium and another one is chemical equilibrium. So we are going to study in detail about physical equilibrium in this session. So the equilibrium in which the two opposing processes means just now we discussed it's a reversible reaction. One will be in the forward direction and another one will be in the backward direction. Both opposing processes that take place simultaneously. Simultaneously means at the same time it will take place, and equally. The extent to which this reaction is taking place in the forward direction and backward direction will be also equal. Our physical changes is called physical equilibrium. So this reaction is taking place in the forward direction as well as backward direction equally and at the same time, and they are physical changes. They are only physical changes. Then we can say that it is having physical equilibrium. Okay, for example, water and water vapor in equilibrium in a closed container. So this was the example which we have discussed in the beginning, right? So if you have taken water in a container, in a closed container, what happens? Water and water vapor will be in equilibrium. We just discussed now. Water will be getting converted into water vapor by evaporation. Right, okay, or vaporization, and water vapor is getting converted back into water by condensation. So the rate or the speed at which both of this reaction is taking place will be equal and it will be happening simultaneously. Right, now that is why we can say that it is in equilibrium. That is clear. But why exactly we are calling it as physical equilibrium? Because a physical change is only happening here. There is no change in any chemical composition, right? It is getting converted from water, which is in the liquid state, to water vapor, which is in the gaseous state. The chemical composition is still H2O. It is from liquid to gaseous state. That's it. So it's just a physical change. So such processes or such equilibria where you can find that there is a physical change happening, they are called as physical equilibria. Now moving on to equilibria in physical processes, different types of physical equilibria we are going to study. One is solid-liquid equilibrium. It's existing between a solid and a liquid. Again, we can take an example like we have discussed in the previous slide itself. That is solid and liquid. We can consider, yes, ice, water in the solid state. That is ice, and liquid, that is water in the liquid state. The equilibrium in which the rate of melting of the solid, is equal to the rate of freezing of the liquid is called solid-liquid equilibrium. That means if in a closed container, again it is necessary that it should be a closed container, right? Or else the water vapors or whatever it will get escaped from the container. So it must be a closed container and it must be kept under constant temperature and pressure. Again, if we are varying the temperature and pressure, the point at which the equilibria is attained will be different. Okay. So if we are taking a closed container at 0 degrees Celsius. Okay. So at 0 degrees Celsius, what happens? Ice will start melting as well as water will start freezing. Right. Both of this process will take place. That is melting, that is solid to liquid. Ice will start melting, that is ice get converted into water, and water will get converted back into ice by, yes, freezing. Both of this will take place, and this will take place at the same rate. That means the rate or the speed at which melting is taking place, exactly the same rate freezing will also take place. That is what is written here. Rate of melting of the solid, that is the ice, will be equal to rate of freezing of the liquid, that is water. Okay, so it has to be maintained in a closed container at 0 degrees Celsius. Then you can observe this. So when you observe it or you measure the mass of it, there won't be any change of it, and you will feel like that the reaction hasn't even taken place, right? The equilibrium that exists between ice and water is an example. In a closed system at 0 degrees Celsius, ice and water attain equilibrium. At that point, rate of melting of ice will be equal to rate of freezing of water, and it is represented as H2O in solid state, that is ice in equilibrium with H2O in liquid phase. That is, ice is in equilibrium with water in the liquid phase. So what is that you have to remember in solid liquid equilibria? It is rate of melting, right? Rate of melting will be equal to rate of freezing, right? Rate of melting will be equal to rate of freezing, right? Moving on to the next one, that is liquid vapor equilibria. Liquid vapor equilibrium. So this example we have already discussed, right? The equilibrium in which rate of vaporization, that is from liquid to gaseous state, is equal to that of condensation of vapor, is called liquid vapor equilibrium. That is from gaseous state to liquid state back, right? So evaporation of water in a closed vessel is an example. In this process, rate of evaporation will be equal to rate of condensation. So again, in a closed container, we are taking water. What happens? Once it starts boiling or heating, what will happen? Water gets converted into water vapor, and the rate of evaporation as well as rate of condensation will be equal. And then we can say that water in the liquid phase as well as water in the gaseous phase, right? Water vapor will be in equilibrium with each other. So what you have to remember in in liquid vapor equilibrium, rate of evaporation will be equal to rate of condensation, right? Moving on to the next one, that is solid vapor equilibrium. So what is the process by which solid gets directly converted into vapor? It is called as sublimation, right? So the equilibria in which the rate of vaporization of solid, that means solid getting converted directly into gas, right, is equal to that of condensation of vapor into solid. Okay, so the rate at which solid is getting converted into gas, directly into gas, and the rate at which gas is directly condensing back into solid, both of that rate will be equal. That's it, right? Yes, an example for it, the sublimation of iodine to iodine vapor and condensation of iodine vapor to solid iodine is an example for solid vapor equilibrium. Okay, so in this equilibrium, rate of sublimation of iodine is equal to rate of condensation of iodine. So that means that if in a test tube, if you are taking few iodine crystals, okay, we take a test tube and below that and inside that we are taking few iodine crystals. So iodine, what will happen? It will undergo sublimation. That is, this is iodine crystals which will be in the solid state. So it will start evaporating, or it will start getting converted into iodine vapors, that is in the gaseous phase. So what happens? It is a dark purple color. So what happens is, eventually in the beginning you can see a light purple color here, and after a while what happens? The rate of evaporation, that is from solid to gas as well as gas to solid, the rate will be equal. Then what happens is the color will be just the same throughout the test tube. So what can you say? We feel that the reaction is not taking place because both of the reaction is taking place actually, but it is happening in the same rate and simultaneously. So eventually what will be happening? The rate at which solid is getting converted into gas will be more. That is, forward reaction will be more. That is why you will be only able to see a small color here. Later it will be completely purple throughout the test tube. Why? Because yes, the rate of both of the reactions will become equal. So this is an example of solid vapor equilibria, right? Now moving on to equilibria involving dissolution of solids or gases in liquids. Now we are going to study about the equilibria when we are going to dissolve solids or gases in liquids. Okay, so when we dissolve any solid in liquid, what is the equilibria, or how is the equilibria attained? Okay, so what are the forward reactions and backward reaction? How is the equilibria attained? And how, when gas is dissolved in a liquid, what is the equilibria attained? So let's discuss solid solution equilibria. That is, when we are going to dissolve a solid in liquid. Okay, when a slight excess of solid solute is added to a fixed amount of liquid solvent, some amount of the solid solute remains undissolved. It appears as if the dissolution process has stopped, but actually both dissolution and crystallization takes place simultaneously to the same extent, and the system will be in dynamic equilibrium. So what is dynamic equilibrium in detail? We are going to study in the upcoming sessions. So as of now, what does this paragraph say? Let's understand. So in a small beaker or any container, let's assume that we have taken some water. Okay. So let's make it a constant value, that is any value. Let's assume that we have taken 50 ml of water in this container. Now I add few tablespoons of sugar to it. Okay, so what happens if I add few tablespoons of sugar, I mix it will get dissolved. Again and again I am adding, going on adding sugar. Okay, sugar is in solid state, right? We are talking about solid, dissolving a solid in a liquid. Yes, so again I am adding sugar, again I am dissolving it. Okay, again it will get dissolved. Okay, so at if we continue this process, at a point you can observe that now the sugar is not getting dissolved in the liquid. That is, it is not getting dissolved in the water. So what is happening here? It has attained an equilibrium. Now further it is not getting dissolved. Okay, so in the beginning what we were doing, we were adding sugar, we were mixing it, it was undergoing dissolution. So that process is called as dissolution. Okay, that process is called as dissolution. Now what happens to, after an extent, if I am again adding sugar, that is excess of sugar if I am adding, what happens? It won't get dissolved. It will remain in the bottom of the container itself, right? It will not get dissolved. So that is called as crystallization. That process is called as crystallization. So in the beginning it was an unsaturated solution. That means still we could have added more sugar, it would have been dissolved. That is an unsaturated solution. But once that point is obtained, okay, if we add further sugar also, it will not get dissolved. So that once that state is obtained, it becomes a saturated solution, right? Okay, so which are the two processes happening here? Dissolution and crystallization. So dissolution means the solid is getting dissolved into the liquid. Now crystallization means the sugar which is present in the solution, right? In the solution, it is crystallizing back into solid. So both these processes are happening. Solid is getting dissolved into the liquid, and the solid which is present in the liquid is getting crystallized back into the solid. So when you observe again and again, if you are adding sugar, no other change you will be able to observe. You will just see that the sugar is getting deposited in the bottom of the container. But what exactly is happening? Did the reaction stop there? No. The reaction is happening here. Crystallization process is taking place. So we can say that the system has attained equilibrium when the rate of dissolution will be equal to the rate of crystallization. Right, rate of dissolution will be equal to rate of crystallization. So I hope it is clear. Thus, the equilibrium in which the rate at which the solute particles go into the solution, that is the dissolution process, is equal to the rate at which solute particles in the solution get into the solid phase, that is crystallization. So when that rate becomes equal, we can say that they are in equilibrium. So example of sugar which is in the solid state and sugar in solution phase, that is which is already present in the solution. Okay, so I hope it is clear. Now next one is gas solution equilibrium. So dissolution of a gas in a liquid. Okay, that is any liquid. The equilibrium in which the rate at which molecules of a gas go into the solution phase is equal to the rate at which the molecules of the gas in the solution phase go back to the gaseous phase is called gas solution equilibrium. So one example we can take is of carbonated drinks, Coca-Cola, 7-Up, any carbonated drinks. You can see that once you open the lid, yes, with a fizz sound, some gas will come outside. So what exactly is that gas? That is carbon dioxide gas, right? So carbon dioxide gas is present in the solution, that is in your Coca-Cola, 7-Up, whatever it is present in the solution, right? So where you can identify this equilibrium, the equilibrium will be between the carbon dioxide gas which is present in the solution, that is in your liquid, which is dissolved, right? Carbon dioxide is present inside the liquid in the dissolved state. Yes, and that when we open the lid, it is getting converted into its gaseous phase, right? So there exists an equilibrium between the carbon dioxide in the gaseous phase and carbon dioxide which is dissolved in the liquid. right? Okay, so to how much extent or how much mass of carbon dioxide we can dissolve in the liquid is based on a law which is called as Henry's law. So Henry's law states that the mass of a gas dissolved in a given mass of a solvent is proportional to the pressure of the gas above the solvent. So it means that why when we open the bottle we are able to hear that fizz sound and the carbon dioxide gas is coming out of or coming out all of a sudden, because it is present that the carbon dioxide gas is being dissolved in the liquid under very high pressure. So suddenly when we open it, the pressure is coming out, the pressure is becoming low, and the gas, you can see that it comes out, right? Okay, so that is based on a law which is called as Henry's law. So when we increase the pressure, as the pressure becomes more and more mass of carbon dioxide we can dissolve in it. Okay, and hence what happens is solubility. Solubility means how easily the carbon dioxide can get dissolved in the liquid, right? That will also increase. So that means if you are increasing the pressure, okay, if you are increasing the pressure, what happens? The solubility will also increase. So it will easily get dissolved in the liquid, the carbon dioxide gas, and easily more amount or more mass of carbon dioxide also we can dissolve in it. Okay, so when the carbon dioxide in the gaseous phase, right, and the carbon dioxide in the solution phase, they will attain a equilibrium with each other, right? So I hope it is clear. Now moving on to the general characteristics of physical equilibrium. Equilibrium is established only in closed system at constant temperature. So this is very important. It is only attained in a closed container. So if it is open container, what happens? If evaporation or condensation process is happening, it will all escape out, right? It should be in a closed container, and it is necessary that it must be at a constant temperature and pressure. If we change the temperature and pressure, yes, of course, the point at which or the temperature and pressure at which the equilibrium attained will be different, right? The next one is all measurable properties of the system remains constant. So once the system has attained equilibrium, the measurable quantities, the pressure, volume, temperature, mass, all of that will remain a constant, right? Now both opposing processes occur at the same rate. Okay, so we have already discussed that there will be a forward reaction and there will be a backward reaction, and the rate or speed at which the forward reaction is taking place and the backward reaction will be taking place will be equal. The rate will be equal. Okay, now when equilibrium is attained, it is characterized by constant value of one of its properties at a given temperature. So at a given temperature, it will be a constant value. So I hope the characteristics is also clear for you. So in the next session, we are going to discuss about the next type of equilibria, that is chemical equilibria, and the details of it, right? So I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.